Chapter 1, Problem 76. So here we have freshwater and seawater flowing in parallel horizontal pipelines connected to each other by double U-tube manometer as shown. So here's one of the U-tubes, here's the other U-tube. We want to determine the pressure difference between the two pipelines. Take the density of seawater in the manometer to be 1,035 kilograms per cubic meter. Can the air column be ignored in this analysis? So in this situation, we have freshwater and we have seawater, and these are at different pressures. So we're going to call P1 the pressure in the freshwater tank, and we're going to call P2 the pressure in the seawater tank. And here you can see we have different liquids. We have freshwater here, we have mercury, we have air, and then we have seawater. So we need to look up all of those densities. So the density of seawater is given, but we have to look up the density of mercury, freshwater, and air. So here, let's start at the freshwater tank, and then what we'll do is we'll keep track of the pressures as we go around the double tube U-tube to the seawater side. So we'll call P1 the pressure in the freshwater tank, whatever that is. So here we start here, so we're going down. So we're going to add, we'll call HW the height of the water, the fresh water. So it's here we have plus density of water, GH water. Then we're going down, so we add. And then we notice here this is a U-tube, but the pressure at this point is the same as the pressure here. Remember, it's at the same depth, so therefore we can just jump across here. And then we're going to continue on. We're going to go up now, because remember we're going to travel from the freshwater to the seawater, traveling around, keeping track of pressures. So we started here in the freshwater. We call this P1. We go plus density of water G times the height of the water column, which here is 60 centimeters. Then we're going to jump from here to there, as we talked about. Then we're going to go up, so we subtract the density of mercury times G times the height of this mercury, which is 10 centimeters. Then we're going to continue up to this point here. This is air. So we have minus density of air G times H air. And then we're going to jump over here across because same height. Then we're going to subtract, so we're going to add the density of seawater, G times H of seawater. Then we're going to get to the seawater tank, and we'll say that's the pressure P2. So right away we can look at this. We know all the different values. We could plug in, for example, the HW, that's 0.6 meters. The height of the mercury, that's 0.1 meters. The height of the air, that's 0.7 meters. The height of seawater, that's 0.4 meters. And we know all the densities. So we can solve for the difference in pressure. P1 minus P2, or P2 minus P1, probably the easiest to solve. If you just take this term and shift it over to the right. But looking at this, I mean, if you look at these densities right away, you can notice that since the density of air is 1,000 times smaller than the density of water or seawater, it can be ignored here. The column of air is comparable to the other column heights, so therefore we're just going to ignore this term. We're going to just cross it out and ignore it. So we can plug our values in. P1 minus P2. We can solve for the difference in pressure. We can plug in the G is 9.81. Plug in the densities, plug in the heights, and we get 3.39 times 10 to the third newtons per square meter, which that's a Pascal. 1 Pascal is 1 Newton per square meter. So that's 3.39 kilopascals is the answer here.